Whoa, that's bright. Hi, everyone. I think that's my cue to begin. My name is Alina. I'm happy to be here. I was also here last year for the first time at DevOps Trends. You were all very nice and kind to me. I had a great time, and I'm planning to have it again this year, and I hope you will enjoy this time at the conference as well. Is something wrong with the screen? It's not coming up. Okay, let's pray in the meantime. Okay, in the meantime, maybe I can tell you an overview of how this is going to go. So we only have 45 minutes, and I want to show you a lot of things and tell you a lot of things. So if that's okay with you, we will not do any slides. We will just do a couple of charts, and the rest will be demos and me showing GraalVM in action and things that you need to know to actually confidently use GraalVM in action. Now, with that, my screen is on. Perfect. And if that's okay with you, I will sit down because standing for 45 minutes, that is not for the faint of heart, but hopefully you can still see me and hear me okay. So this will be our little agenda for today. We will talk about all the practical aspects of GraalVM, and namely native image, and all the things that you need to know about it to confidently use it in production, namely how do you build applications, how do you deploy them, monitor them, and optimize for the best peak performance. Now, I will not ask you anymore if you have heard about GraalVM, because we've been doing this for many years, so I hope that by now you have at least heard about it. But can you raise your hand if you have tried building something with GraalVM native image? Okay, I would say at least 1/3 of the room. Very cool. Okay, so this will be our agenda for today. Let's see. And super quickly to get us out of the way, so if you want to do Java with GraalVM, you can do two things. You can run applications on GraalVM Jet as the JVM, and it's important to remember that with GraalVM, you always have that JDK with you. So we are not replacing JDK with native image. We are just adding on top of JDK other capabilities. So you can ahead of time compile your applications, or also with GraalVM, you can extend your Java applications with other languages such as JavaScript, Python, etc. So this slide is my answer to this sometimes kind of like tricky question that I get at conferences. People like asking me when not to use GraalVM. So like when is a bad time to use GraalVM? And my answer is always use GraalVM, but decide for yourself what fits better your use case. So if I want to have a very easy migration path, and if I want to have maybe 10, 15-ish% performance improvement on the JDK, I can go with this first path where GraalVM is my JDK. So I just replace my JDK installation with GraalVM. And in that case, I can expect that around 10-15% performance improvement because we have a new highly optimizing JIT compiler that we have developed ourselves at Oracle Labs. Or I can do another thing. I can go ahead with this ahead of time native image compilation where I can take my Java app and compile it ahead of time and then have it deployed as a native executable. So super quickly about how native image works. So when you run our native image command, what it does, it looks at your project as a whole, and it's trying to find all the reachable code. So all the code that is actually needed for your application to perform what it's supposed to be doing will be put into that native executable, and then we will strip away the things that you don't need. And this applies both to the things that you wrote yourself, so what we call user code, but also to your dependencies, JDK classes, etc. So we will look at your project as a whole and then strip away things that you don't need and only put the code and objects that we think are safe to initialize at build time. We will put that into that native executable. And because this happens ahead of time, obviously it has to happen under a closed world assumption. So everything that there is to know about your application needs to be known at build time. Okay, good time to update my machine, not now. With that quick intro out of the way, let's look at our first demo. So the first thing we will run will be a dictionary application, and we will look inside in a sec, but let's just run it and see how it runs. So it's a Spring app, so I can just run it like this. And it takes a little bit to start, and then it starts in something like 2 seconds maybe, and then if I go to the endpoint, it's a dictionary app, and it exposes a translation endpoint. I see something like this. I could have asked you what do you think this language is, but I will not torture you with guessing. I can just give you the answer. This is Swiss German. If you happen to be into languages, it's very fun to look into. Also, if you maybe speak High German, so Swiss German is very interesting, very cute. I encourage you to look into it. So this is my Spring application. And if we look inside the project, it's a fairly standard, trivial Spring app. Let me just move this down. So here are my Spring, where is it, dictionary? Here are my standard Spring classes. I have my controller that we have seen. I have my repository. And then our data, our actual translations are stored in H2. And for the project structure, this is my POM XML. So again, nothing too weird, pretty standard Spring things. I have my Spring Boot data, Spring Web dependencies. I have my H2 somewhere here, and my Spring Boot Maven plugin. So all pretty standard, all nothing too weird here for now. But let's say we want to move this existing Spring application to GraalVM. So how would you do it? Now, if I had any other project that isn't Spring, my standard approach would be to go to native build tools. And this is the website here. And those are Gradle and Maven plugins developed by our team. So the way I would move any project to GraalVM is I would go here, and maybe I want to start with Maven because I do like Maven more. So my number one step would be to add this native Maven plugin, and this is a plugin that will help me build my application, build it, test it, but also configure libraries and help use libraries in native image mode. So I would start here, but as a Spring user, I can also do a different thing, and I can go to statusspring.io, add dependencies, and I can see here native image on the very top. And then if I go to explore the project, I see this native Maven plugin, so the same plugin here. And this is statusspring.io, but you can see that the plugin is ours. It's coming from the GraalVM team. So the Spring team is nice enough to include our plugin as a standard configuration way to configure native image. And this is very nice if you happen to be a library or framework author to include this plugin from our team as a kind of interface to native image, because this can be a nice unified way to configure all things native image. So let me get this plugin from here and add it to my project. Okay, looks good. Now, I could have left it as is, but I also want to use this opportunity to show you how I can configure additional things here. So if I need to configure anything about my native image build, I can add this configuration block inside it. And this is a more generic configuration section where I can configure more things, such as image name, etc. But let's say we want to pass any random argument to it. So for that, I would add build args, and within that, I can add an individual build arg, and this is my way to pass any options and configuration parameters to native image. So here I want to do -OB, and this will be quick build mode. So let's say this application is not being deployed yet, I'm still working on it, and I don't care about peak throughput at this stage. I just want to compile it and see whether it compiles and whether it works fine. So let's compile it. Let's clear this, and let's do Maven p native compile. So the way this quick build mode works is that it will not apply all the compiler optimizations. So my application will not be as fast with this option as it would be out of the box. And this is more of a development tool saying, I just want to verify the application is still functional. Don't apply that many compile optimizations. Just let me verify that my build still works. And as it builds, we are starting to see some information coming in about our machine, about what kind of optimizations we are applying, how much memory it detected, and how long it will take to build the application. And when I show this on the stage, usually that's the stage where people come to me and say, Alina, oh my God, this build is taking so long. Why does it have to be that long? I don't have that kind of attention span. Guys, do something about it. And I'm with you. I also don't have that kind of attention span. But check this out. So we've seen that my application has maybe like 5 classes that I have wrote myself. But because under the hood, I also have JDK, I also have my Spring dependencies, etc. Indeed, this project as a whole contains 33K reachable types and then 187K reachable methods. So methods that are actually used in my application and they are doing some meaningful work, as opposed to, let's say, 289K methods in total. So JDK gives me, and Spring and other dependencies in the Java ecosystem, they give me good peak throughput, they give me good developer productivity, all the nice tooling and capabilities, but it comes at the cost that under the hood there is all that machinery providing that peak throughput and that productivity. And that is why native image might take a while, because it needs to understand what is your project actually doing and which parts of it are critical for the application behavior. Now, as I was chit-chatting, in the meantime, my app compiled in 1 minute. Now, without the quick build mode, this would have been maybe 1 minute, 30 seconds. So it doesn't speed up the build like matter of times, but it's still a nice development tool to make a build faster. And I have some random files generated courtesy of AWT, but what I actually need is this dictionary executable that we have over here. And I can compile it like so, not compile, run, target dictionary, and then the JVM version was starting in 2.5 seconds, I think, and this one just starts in 141 milliseconds. And if we go back to the endpoint and open our translations, we see that the output is the same. The application is still fully functional. Now, startup is just one part of what native image can give you. Here, I could have measured also CPU and memory consumption, but I would like to do it a bit later when we are doing performance benchmarking. But if I measure the memory usage right now of both processes running on the JVM and running with native image, I would see that my JVM process would take maybe 500-600 megs of RAM, and then native image out of the box without any limitations would take 100-150. And obviously, this memory requirement would grow as you grow the load on your app. But on average, from my observations, you can expect at least 3x less memory with native image as you would have was using using your application on the JVM. OK, so this is how you would move your existing app to GraalVM. And let's talk about more things. So let's say I convinced you and you want to try to build your project with GraalVM native image, but then maybe you have tried or maybe you have heard that not all libraries are compatible with native image yet. So how can you make sure that your project will work with native image, and how would you make those libraries work? And then when talking about libraries, often the candidate for where those issues or challenges might arise is things like reflection, because reflection in its nature, it's very dynamic. So it's happening and is resolved at runtime. And as we talked, native image compiles the application under closed world assumption at build time. So those more dynamic Java features, namely reflection, serialization, proxies, GNI, etc., they work with native image, but they require some kind of configuration for native image to know to include those specific features in your application. And that configuration can be coming from you, from your library, from your framework, maybe without you even realizing it. But the long story short is native image can do pretty much anything for you as long as you can tell it exactly what it needs to do and exactly what needs to be included. And in a way, this can be seen as limitation. For example, if I want to do a more advanced reflection call, I need to instruct native image. Maybe it's a bit, cumbersome. But I think it's also a nice, I would say, security perk and security upside of native image, because none of those more dynamic Java features can happen at runtime unless you explicitly allowed it. So you have more awareness and more control of your application and what exactly happens at runtime. So let's talk about how you can use libraries with native image. And this section maybe will be a bit less fun, less, entertaining, but it will be useful if you want to use libraries with native image. So each bullet point will be a complete solution to using libraries. And by libraries, I mostly mean libraries that are using reflection. So each bullet point here will be a complete solution, how a library can work with native image, going from the best case scenario down to the scenario that requires a little bit more work from your side. So first thing is a library can be compatible with native image, such as maybe not using reflection so heavily out of the box. And this is a new trend, but we see more of it lately. Like some time ago, I saw this announcement on social media from a library author saying that they are launching a new library, and they are saying here, no reflection, GraalVM friendly, out of the box, etc. And this is good for native image, but also in general, reflection is very good and useful and powerful. But there are also some considerations and some opinions that when used too heavily, it can add to the overhead of your application. So by using maybe less reflection, a library can be more friendly to GraalVM, but also it can be more kind of lightweight and fast out of the box. So this is obviously an ideal case when the library is designed GraalVM friendly out of the box, but clearly there were many libraries before GraalVM became popular, so what to do about that? In that case, if a library is using reflection and those other dynamic features more heavily, the best thing to do will be to make library compatible by including config within the library itself. And in this dictionary application that we saw before, I was using H2, and I like this demo because in the past I had another demo where I was using H2 and it would break because it could not figure out how to work with reflection, and I would show how to fix it. But now I don't have to do it anymore because if I go to the H2 source code on GitHub, I see that they have this reflect config JSON file within the H2 sources itself. And this is the best way to make a library compatible by just shaping those config files inside the library. So this is in a known reflection, and native image is instructed to look in this location for any config files. But also, we know that, again, not all libraries can add support for GraalVM immediately. Some of the libraries have not so big open source team behind them that maybe have other priorities. So what to do if a library doesn't have config included, like here in H2 case? You would think that it would be nice if some generic config was needed, if there existed something maybe like Maven Central, but for native image config, where let's say if I figure out config for H2 or for something else, person next to me didn't need to figure out the same thing. They can just reuse what I have figured out as config. And we thought the same, and together with our community members, we have created this repo on GitHub, where our community contributes configuration for many popular open source libraries and frameworks. And from here, you can just fetch that config for a specific version. I don't know, let's look at Mockito here. So for each version, there exists config in this repo on GitHub. And the best thing about it is that you don't need to do anything manual with this repo. If you are using our Maven or Gradle plugins, they are instructed to go here and pull config for the libraries from this repository. That's why I was saying that if you want to move your application to GraalVM, the best first step will be to include our plugins, because they will also help you resolve config for your libraries by pulling this config from this centralized place. Now, we covered those first 3 bullet points, and if you are starting a new application right now in 2025, I would say that you will never need to do any kind of manual configuration. If you're using compatible frameworks and libraries, which are most of frameworks and libraries out there, you will be covered by those first 3 bullet points. And if you want to very quickly see if you can move your application to native image, if it will be compatible, I would still add a plugin and just try it compiling. But if you want to have a very quick assessment, another thing you can do is we have this page on the website where we are tracking, our community is contributing to this list. We are tracking which libraries and frameworks are compatible with GraalVM and how exactly. So either through our repo on GitHub with config files, or they ship config ourselves. So here, if, let's say I want to look for something, let's say test containers, I can find them on this page and see that there is config existing for this version and higher. So if I want to very quickly assess my project and see if it would work, one thing I would do if I was, for example, if I had doubts about some particular dependency, I would go to this website and I would check if my library is on this website. Now, if it's not here, it might still work, but those are known bulletproof to be working and testing with GraalVM. Now, getting a little bit into the woods, so let's say you work, I don't know, at a bank and you have some proprietary library that doesn't work with GraalVM, and obviously there is no config for it out there because it's proprietary to you, it's internal use. What to do in that case? In that case, one thing is helpful if you are on a version of a framework that is friendly towards GraalVM and native image. So here in this native Spring Boot repo, I have this interesting case of a reflection controller where it's trying to go ahead and fetch this message field from a message class over here. But you can see that it's doing so in a slightly maybe weird and confusing way. And this is to try and confuse and outsmart native image, because if this was done more trivial, things like class for name, native image does know how to work with some more simple reflection calls out of the box. So here we are intentionally trying to confuse and outsmart native image. And the way to make this work is, for example, here I'm on a version of Spring that is friendly towards native image, so higher than 3.0, which was released, I think, like 2 years ago on something. And there I have support from my framework to make things work specifically here for reflection. So what I can do is I can use this annotation register reflection for binding and pass that class where that reflection should occur. And in this case, Spring, and namely the Spring IoT part of the Spring framework, will look at that message class and will generate those configuration files for me. So this is one way that you can do to kind of programmatically generate config for native image, but hopefully you will never have to do anything like this. This is only if you are using some library that doesn't work with GraalVM and you want to make it work, but those mainstream libraries should work through those first 3 bullet points. Now, if you also are on an older version of framework or somehow you cannot leverage any framework support, you still have one more option that is a semi-automatic configuration generation, and that is native image comes with tracing agent, and you can run your application on the JVM with that agent attached to it, and it will observe what your application does in terms of reflection, serialization, proxies, all of that, and it will output that config files for you. But you do need to hit that application running on the JVM with the relevant workload so we can see exactly what it's supposed to be doing and generate configuration for those cases. And lastly, you can obviously write JSON files yourself manually, but this is way less exciting. So again, for the new project, I would say you will have your configuration coming from somewhere automatically. And then if not, look if your framework offers support for programmatic generation of those configuration files. Now, this was maybe a bit less interesting, but needed if you will use libraries with GraalVM. And now let's talk about a topic that I really like, and that is peak performance optimizations. So we all work in the JVM space, and we love our peak performance on the JVM, how fast our applications are, what an amazing latency they have. So what about native image? Many times you will hear an opinion that, you know, IoT compiled code can start fast, applications are small, but it will never be as fast as dynamically executed code on the JVM. So let's see that in action. And here we could have benchmarked our dictionary application, but honestly, it's quite simple. It's just one endpoint, and you can tell me that I micro-optimized that one endpoint in the native mode. So let's see if we can do a bit more elaborate benchmarking. For that, we will take a look at the Spring Pet Clinic application. I will not start it for the sake of saving time, but this is this fairly famous Spring web app that replicates this kind of enterprisey patterns and behavior, where it's an application of an imaginary pet clinic, and there you can create owners, create pets, read data, write data, schedule visits, look at doctor's information, etc. So it replicates as much as possible those kind of enterprisey Spring web apps. And we will benchmark it on the JVM and with native image. And our benchmarking setup will be as follows. Now, stay with me because this will be a bit elaborate, but if you want to have a proper benchmark or like conference proper benchmark, this is the closest we can get. So what we will do here, we will start our application on the JVM, and my script is called bench.jit-c2. So here I will be using GraalVM, but I'm turning off the GraalVM compiler, so I will be using C2, your standard OpenJDK JIT. Then I'm using a tool called PS Record to observe resources consumption of my process. Then we are starting the application, and we are waiting 10 seconds to give the application a chance to even start. Now, in my observations, it starts in maybe 5 seconds, and you can see it later on in the charts. But just to be on the safe side, we are waiting 10 seconds. Then we are warming the application up, so we are sending the load, but we are not looking at those results yet. We just want to warm up the JVM. And then finally, for 20 seconds, we are sending the actual load that we will be considered the benchmark. So let's start it, and let's start with our JIT setup. Now, as this runs, because this will take 40 seconds, because that's the duration of the benchmark, I will show you the actual load that we are running, because we talked about the methodology, but not about the load yet. And the load is defined in this Lua script, and it's again meant to replicate possible human user behavior. So instead of starting the app and just bombing one endpoint with crazy amount of requests, we are sending this sophisticated load where we are creating a new owner, then we are creating a path for that owner, then we are trying to read the owner data, then we are trying to schedule visits, etc. So we are trying to hit different endpoints with the load and also read and write data. So this is a bit more advanced and a bit more fair as a benchmark. Now, again, proper benchmarking will take many hours, but for the sake of a conference demo, I would say this is a decent enough benchmarking setup. Now, the results are back. We waited 10 seconds, and then we warmed up the JVM, and we see that in the warming up round, it was at 600 requests per second, but we know that the JVM warms up over time, and then as it was warmed up, it has arrived at 1.5K requests per second, so quite faster, 3x faster comparing to the warm-up round. But this is the JVM. Let's see how the native app compares. For that, let's run bench native, and that's a very similar setup, only then we are running a native application with the exact same setup, waiting 10 seconds, warming up, and then benchmarking. What's funny, native image doesn't need those 10 seconds to start. As we have seen, it's very fast, but we do have a very similar setup, so we can compare like apples to apples with the same setup as we had for the JVM. So as this one runs, who thinks this will be faster than the JVM? Quite skeptical people in the room. You know, I work on GraalVM, so I could have applied some nasty tricks to kind of make it look faster, you know. You don't have a lot of faith in me, but let's see. So this is done actually as we were talking, and we can see here that the JVM finally was in the beginning at 600 requests per second, and then it arrived at 1.5 requests per second. Now, the native application, it was not warming up, so it was actually ready to serve good load from the very beginning. It was at 1.2, so twice as fast as the JVM, but then it did not exactly arrive at quite the same peak performance numbers, right? So it stayed, I would say, very fast, but very steady over time, and still a bit slower than the JVM. Now, here I could have said that, you know, but native image application starts fast, doesn't use that much memory, it's very hard to be in the JVM at its own game, you know, like it's a masterpiece of engineering, all of that. I could have said all those things, but still I believe we can do better. So let's see if we can do better. And for that, I will use one more version of this application that is called Bench Native, and that is native optimized, and that's also a native application, but compiled with a few additional optimizations. Now, as it runs, what are those optimizations? Peak performance. Here we are. So if you want to have good peak throughput on native image, the number one thing that you need is PGO. PGO is profile guided optimizations, and you might know how the JVM profiles your application as it runs. So the JVM looks at your application and it's analyzing constantly which parts of your application are warm, which methods are warm, which loops are more often executed, and where it makes sense to execute those compilation efforts, because those parts of the application is where that critical work is happening. And that is the argument that I sometimes get from people, but that native image doesn't have that runtime awareness that the JVM has. We saw the same thing, so we implemented PGO in native image, where you can build an instrumented version of your application. So you need to do two runs. First, you build an instrumented version of your application, then you start it, then you run it with relevant workload, and you basically show us what the application is supposed to be doing at runtime. And when you shut the application down, we will generate a profile files similar to what the JVM does. So we can collect that runtime information about your application and see where it makes sense for us to invest compilation efforts, kind of like the JVM does. And here you can tell me that the JVM profiles all the time and it can optimize all the time. But the reality is that the JVM optimizes and profiles quite heavily in the beginning, and then it does profile over time, but mostly when something critical happens, then it introduces changes. And native image does the same thing ahead of time, but also we have this closed world assumption. So in a way, we have a more complete view of your application because we know exactly what will happen at runtime. And those things that are not allowed at build time cannot happen at runtime. So in a way, we have a more complete view of your application that lets us also optimize good for peak performance. Now, that was PGO, and in case you don't want to do this like two-step process where you collect profiles and then you build again with profiles, you would think that everyone does ML nowadays, and wouldn't it be nice if you could use some kind of ML to predict your application's profiles and not have to do this two-step process. And we saw the same thing, so we included in native image this tiny little ML model that if you don't give us profiles through this manual process, we will analyze your application and we will try to predict, to infer what your application will be doing, and then optimize application based on those predictions. And this obviously will not be as good as actual user collected profile information, but this can give you 8-10% performance improvement out of the box. And I would say that for like one-step build, an easy setup process, having 8-10% is still good. Now, two more performance optimization options. You can use different GCs in native image, but for good peak throughput, most likely you will need G1 GC. You can also use serial, etc. But in our observations, G1 GC is usually very good for peak throughput with native image. And then you can use this last flag called mArc native, and that will specialize a native executable to make the most use of a machine where you are building it. So native image always builds applications that are specific to an operating system and architecture. So let's say I cannot build on my MacBook for Linux, or I cannot build on my ARM Mac for an Intel Mac. It will be always the same operating system and architecture, but you can additionally instruct native image that I will not be distributing my executables throughout similar machines in that architecture. It will always be running on a similar kind of machine. Please make the most use of the hardware of this particular machine. Now, with all that chit-chatting about peak throughput, let's look at the numbers. So with PGO, G1, and mArc native, we have arrived at 1.8, 1.5, 1.6K requests per second, so very on par with the JVM. So clearly, this is a tiny little benchmark, and I'm supposed to tell you all this legal disclaimer that please, look at those numbers carefully, do your own measurements, etc. But this is to show you that by applying additional optimizations, if you know what to do, you can also get very good peak throughput with native image, in addition to that fast startup, low memory usage, security, etc. But this is peak throughput, and as we were running our application, we were also measuring how many resources it was consuming. So let's look at that, because this is also interesting. AUT performance, this is our run, and let's look at the numbers. So this is my application running on the JVM, and let me just open the rest, and then we will compare them. And native optimized. So what we are looking at here is charts coming from that tool that I mentioned in the beginning called PS Record, and this is measuring my applications as they were running in this benchmarking setup. And the way to read this is the red vertical lines is CPU usage, and the blue horizontal line is memory usage. And several observations here. So on the left, that's the JVM version, and we can see that indeed for the very first 5 seconds, it was starting, and it was quite busy, loading classes, interpreting, compiling, etc. Even before we send the actual load to the application, the JVM needed to do a bit of that housekeeping work to make it happen. And then for the rest of the 5 seconds, it was just waiting for the load to come. And then when the load actually comes, it's once again very busy, and memory even goes a bit through the roof, even though all 3 applications ran with the same memory settings. Now, what about native image? So as I said, we were waiting 10 seconds with native image, even though we didn't have to, because we wanted to have the same setup as with the JVM. But we can see that it started in the beginning, in the very first couple milliseconds, and then it's just idle and waiting for our load to come. And here we can see that both CPU and memory usage are lower in our both cases, but memory usage is a bit higher on the optimized version of a native image comparing to native image out of the box, because if you are using G1 GC, it's more or less expected that your memory usage will be a bit higher than, again, a normal native image application, but still lower than on the JVM. because if you want to have more peak throughput, it's more or less expected that you need to trade in a little bit of memory for that more peak throughput. Now, that was maybe a longer demo, but hopefully it showed you that you can have good peak throughput with native image if you know which optimizations to apply. Okay, and I see that I have less than 10 minutes, so maybe we need to prioritize which demos we want to see. So we can take a look at a monitoring observability demo with micrometer, or we can do a security demo. So who wants to see micrometer monitoring demo? Okay, I think that's a majority. I'm not even gonna ask about security, but if we have time, I'll see if we can also see the security demo. Let's see. Let me just navigate to the right place. Okay, let's clear this, and let's go to our observability demo. Okay, and I need to start this thing, and then we will talk about what's in it. Compose up D. So what we will take a look at here is two applications compiled with native image, and then we will see if we can observe them and collect metrics, logs, and traces for those applications using micrometer. So right now I have started my observability backend, and now I need the actual applications so we can take a look at them. And I have them already compiled. So here in my shell, everything compiled to native is green. So this is my server app. We can start this one. And we can go ahead and start our client application. Client target client. No, not classes, client. Okay. And as I started this, you can already see that there is some kind of interaction going in those two processes. So one is a natively compiled Spring application with micrometer added, and that's a client app. And in the middle here, it's a server application. So a client is sending requests to the server to fetch some information about a user, and then a server is responding to those requests. And this is using the micrometer project that happens to have a very nice support for native image. Where is it? Micrometer. So it's a nice kind of standard observability stack and framework for many frameworks out there. In my head, it is somehow connected to the Spring ecosystem, but in fact, it is framework neutral. So even Micronaut, from what I know, has a nice support for micrometers, so you can use it from many different frameworks. And what it does, it collects data about those two native applications and then sends them to our observability backend. Now, I hope this was enough time to send data to our observability backend. Let's see if we can actually get it. So that will be dashboards. Okay. Yes, I was talking long enough. So here we see actual data coming in from our system. And this is, for example, our client application that has got response from the server. And then we can explore it some more. So here we can see that our client app has sent a GET request to our server. We can see how long each operation took. And here you can see that also server fetched that information about a user and send it back to the client. And here we can explore more things. We can take a look at the logs for that specific trace. I think this is zoomed out a little bit. Yeah, so we can explore more logs here in this view. Or another thing that I wanted to show is we can explore our system. In our case, it's not that complicated. We only have a client and a server application. But if our system was a bit more complicated, we would see how all those different nodes interact along with those request times. And we can also fetch more info here, such as request rate. So we can see here over time how many requests per second our system serves. So here it's around 3.5, I would say, requests per second. So it's a very nice way to monitor native image applications and have insights into your system, but that is just one way to do it. So this thing we were looking at was micrometer. Let me just scale it down. But also you can use other standard JVM tooling such as VisualVM, JFR, JMX, etc. With native image, there exists support for all those protocols to different extent. And another thing for if you happen to be a real performance geek, you can also use Linux tooling, for example, things like perf, because in the end you have a native application and you can observe the application as a native program. Now, I will not show a security demo because I want to show you also what I've been working on and what you can expect in the future from GraalVM. But just to talk about the security angle, so I mentioned that we limit in a way reflection, serialization, etc. And that is just one security angle in native image. But also we have support for things like SBOM. So what you can do, you can build a native executable with SBOM, and then you can use your vulnerability scanners of choice. For example, I like GraalVM. And then you can scan your native executable as any other program, and it will tell you which dependencies are inside, whether or not there are vulnerabilities, so you can maybe a bit more confidently deploy such application in production. Now, let me talk about some of the fun things that we are working on for the future and what you can expect coming up in the future from the GraalVM team. So maybe the biggest project that we're working on in the native image space is called native image layers. And right now, the idea of native image is that you compile your application and you put all that you need inside that native executable. But we are exploring a different thing where you will be able to compile native image applications as, in a way, like you can think as like Docker layers almost, where I can, for example, say that this is my application code and I can compile my dependencies, the things that I'm using, as those base layers and use them almost as shared libraries. So every time I need to introduce changes to my application code, I'm only recompiling this application code, the layer that I have wrote myself, and the base layers stay compiled, so I just use them linked. And this gives me faster build times, so we believe that application compilation times will be a matter of seconds, but also once I deploy my application, I can reuse those base layers to run multiple instances of my app and benefit from memory sharing of the base layers. That is one big thing where we are working on. The next thing will be called Project Crema, and we are considering adding a base layer as an interpreter, so you will be able, in the native image, also load new classes. So there no longer will be this limitation on the closed world. You will be able to load whatever you want at runtime if you will be using Project Crema. Another thing is called Preserve All. So we are working on this project where if you want to, you can pull literally everything from your project into a native executable. So not strip away anything, but literally put everything that there is, all your JDK, all the dependencies, etc. And then this native image will be a bit larger, but also it will compile out of the box. You will never hit any issue, any problem, and you will still win startup times, memory usage, etc. But you will have a slightly larger application. But we saw a request from this in our community where they want to just build an application, doesn't matter if it's large. So this is one area where we are doing exploration. And then we also can embed multiple things in a native image. So we can also run JavaScript, Python, etc. You can include those languages in the native image as well. And there you can produce some fun, for example, charts using Python charting libraries. And the last thing I want to show you is this very fun project we have deployed on the GraalVM website called JavaC on WebAssembly. So what is this? So native image outputs a native executable, a machine code, but technically nothing prevents native image from outputting some other formats of code. So there exists this experimental WebAssembly backend for native image, which means that you can take JVM bytecode and compile it to WebAssembly. This is still early days, this is still experimental, but the thing that we are looking at here, which looks like a simple HTML page, is indeed the JavaC, so the compiler that we are using to compile source code to bytecode. We have compiled it to WebAssembly because it's a Java program, and we have deployed it here to the GraalVM website. And to show you that this is live, I can actually do some changes here. So maybe I want to say, I don't know, hello from Paris, and I can even add some emojis here, and I can compile this. So this is a fully functional JavaC running as WebAssembly. And to prove to you that this is real, I can disassemble it, and I still see some instructions. For example, here I see that my string was fetched, then the print line statement, there my string hello from Paris. So early days, experimental, but eventually we believe that we will be able to compile more and more JVM applications to WebAssembly, so stay tuned. With that, I want to wrap up. I have exactly 3 seconds. So if you want to get all the demos that I have showed here today, you can get them from GitHub. This is my page. And in case you have questions, I will be here during the break and the rest of the day and also tomorrow. But you can also find me on Blue Sky if you want to follow up. If you want to ask for slides, maybe I can also give you slides. With that, I'm open to questions, and I will let you get your lunch. I just want to say thank you and ask you to ask me questions and provide feedback. Thank you so much.